In this lab, you will be working with standing waves using a simulation. You will explore the relationship between velocity, wavelength, and frequency of waves on a string. You will also see how these properties are affected by tension and mass per unit length. The simulation allows you to adjust things like frequency, tension, mass per unit length. The simulation includes a standard length in meters. To measure the wavelengths on the screen, you will need to use a ruler. That ruler might be in centimeters or inches. You will use a ruler to measure the reference distance on the screen and establish a conversion factor between your measured lengths on the screen and the equivalent wavelength in meters for this simulation. For example, suppose you measured the 4-meter overall length to be 17.2 centimeters. You then measure the crest-to-crest distance of a wave to be 4.2 centimeters with your ruler. You can set up a ratio that would convert that to wavelength on the simulation. In general, you could use the second equation listed in Excel to convert any length L that you measure to a corresponding wavelength. Once you have your conversion factor, you can start playing with the simulation. You will look for specific numbers of antinodes, peaks or dips, in the wave pattern by adjusting the frequency until you get a standing wave. The number of antinodes present will give you the harmonic number n. By pausing the simulation at the right moment, you can measure the distance between these antinodes using your ruler. You will then use the conversion factor to find the corresponding wavelength in meters. You will repeat the process for different frequencies, going up in sequential harmonic number and recording the harmonic numbers, measured wavelengths, and the corresponding frequencies in your data table. You should be careful to note that you have reached a proper standing wave when the wave has nodes at the pulley location where the string rests on the pulley and at the tuning fork location. It can be easy to be fooled if not careful. After collecting enough data, you will plot the wavelength on the y-axis, the dependent variable, and frequency on the x-axis. If the graph you get is not linear, then use the relationship between wave speed, wavelength, and frequency to isolate wavelength and linearize the data to get a second graph. The slope of this linearized data will be the velocity of the waves, which depends on the constant tension and mass per unit length used in this part of the experiment. Parts 2 and 3 of this lab will follow a similar approach. You will keep one variable constant, either the tension or the mass per unit length, and vary the other. You will measure wavelengths, calculate velocities, and plot graphs to analyze the relationships. If the graph you get is not linear, then use the relationship between wave speed, tension, and mass per unit length to linearize the data for that part of the lab. This will require opening the radical of the original equation. By strategically plotting the data, squaring the velocity or taking reciprocals, you will end up with linear graphs whose slopes should be related to the variable that you kept constant for that part of the lab, the tension or the mass per unit length. What you will submit in your Word document lab write-up. In addition to answering the questions and providing completed data tables, there will be 6 total graphs. In all cases, this would be an original graph of the data that is to be plotted and a linearized version of that data set as needed. All graphs need to be properly done and appear on their own pages, filling that page. So proper title for the graph, proper axes labels, a line fit to the data, either a curve or a straight line, extended to the y-intercept as appropriate, and if you use Excel, an equation for that fitted line on each graph. And you should have a calculations page that includes each of the calculations specified in the analysis section of the write-up.